Yo, what's up, guys? Today we'll be doing implicit differentiation. So, we'll be doing a few examples. I think learning by examples is one of the best ways to learn. And the first example we'll do is the example where we just explaining this. We have to differentiate this using implicit differentiation. So, implicit differentiation is differentiating when normally you can't make y the subject of the formula. I know here y is already the subject of the formula, but I'll show you how you can do this using implicit differentiation. And in fact, almost every time when you differentiate, you can call it implicit differentiation in a way, but there's unique problems that we normally use implicit differentiation for. So for here, if you were using implicit differentiation, what you do basically is you find the derivative of this side and you find the derivative of the other side. The rule is that the derivative of the left is the same as the derivative of the right. So the derivative of y with respect to x should be the same as the derivative of x with respect to x, right? And then we say here this is just the derivative of y with respect to x, which is the same as dy dx. And on this side we use the laws of differentiation. We say, what's the derivative of x? X is a polynomial and it's linear. So since the exponent is just 1, you take the exponent and multiply with the coefficient, you get 1, and then you subtract 1 for the exponent and your answer is 1. Basically, this is what you do when you do implicit differentiation. You find d on dx of the left hand side and find d on dx of the right hand side, and then you can simplify. Now let's do the second example. Second example is use implicit differentiation to differentiate this. On this one, I'll show you how implicit differentiation is the same as normal differentiation. So I want us to first differentiate this using normal differentiation. If we were using normal differentiation, we would do this. We'd say y is equal to plus or minus the square root of x, right? Because if you put a square root this side and square root that side to cancel the squared, but you have to put plus or minus this side. Now, if we were using normal differentiation, you'd say dy on dx. Okay. First what we do is say plus or minus, then you say x to the power of 1 over 2. And then we say, now we are looking for the derivative of this. I know you can separate it and say y is equal to positive x to the 1 over 2, or y is equal to negative x to the 1 over 2, but I'm going to use it both combined like this because it's still going to be plus or minus anyways. So I'll say plus or minus 1 over 2 multiplied by x to the power of negative 1 over 2. Right, I took this and multiplied it with the coefficient, which gave me 1 over 2, and then I subtracted 1 from the exponent, which gave me negative 1 over 2. Now I have the derivative of y with respect to x as plus or minus 1 over 2, this 2, times x to the power of 1 over 2. Okay, there's something I'm going to do here, dy on dx. Firstly, I'm going to say 1 over 2 multiplied by, let me say put plus or minus, the square root of x, right? You understand how the exponent 1 over 2 can be written as the square root. And the second thing I'll do is, I'll say since we have dy on dx, this is 1 over 2 into plus or minus square root of x. Now why am I doing this? This is still multiplied with x, and if there's plus or minus here, it'll make this whole thing a plus or minus, which makes the whole value as plus or minus. Okay, so basically this is still equivalent to this. And the reason why I was doing that was to show you that this right here is equivalent to y. You see, that's y right there. Y was plus or minus the square root of x, which is this. This is still y. Therefore, this can also be written as 1 over 2y. If you use implicit differentiation to differentiate this, you will get this answer. Now, let's get into using implicit differentiation and see how we are supposed to do this in a way that is easier or faster than the way that we used here to get to this answer. So, if we wanted to differentiate y squared is equal to x, using implicit differentiation, we find dy on dx of y squared, and then we find d on dx of x as well. Now, let's start with this side. This is 1. We already did it here. Now let's come to this side. Y is a function we assume of x. We assume that y is a function of x. So if we are looking for the derivative of y as a function of x, we have to use, so we have two functions if y is squared, because the first function is y squared, which is basically the function that's saying y squared. It's saying something should be squared. And inside that function we have a function y, which we don't know. This function y could be x plus 9, this could be cos x, this could be anything. The y could be anything that changes when you change x. So y is not just a value, it's a function. So when we differentiate this, we use the chain rule, because we have two functions. The outer function, which is y squared, meaning something is squared, that's the function, and then the inner function, which is y, and y is changing with respect to x. So how we find the derivative of this is we differentiate the outside. If we differentiate y squared, you have 2y using the power rule, and then if you differentiate the inside, which is y, you're finding the derivative of y. That is dy on dx. Okay, dy on dx. Now let's make dy on dx the subject of the formula. So if you make dy on dx the subject, that means you would just divide by 2y both sides, and you'd have 1 over 2y, which is the same as the answer you got here. Now, me doing this was just to show you that these two ways give you the same thing. But with most equations that you'll be required to use implicit differentiation on, you won't be able to use this method. And therefore, now since you know that the two methods are correct, that means that you know that you can use this one, right? I was just doing this to reassure you that this is a good method, and I should probably do a video on the proof for it as well. But now let's go on to another example. The example we'll do now is y squared is equal to x squared plus sine xy. right? We have to differentiate this using implicit differentiation and find dy on dx. How we differentiate this is we say we want the derivative of this side, d on dx of y squared, and we also want the derivative of this side, d on dx of x squared plus sine xy. Now let's start with this side. Once again, we have y squared. If you have y squared, you differentiate the outside, which is y squared, so you have 2y. And then you differentiate the inside. When you differentiate the inside, which is just y, that will give you dy on dx, which is the derivative of y. Because we don't know the exact value of it, but it is the derivative of y with respect to x. So when we come to this one will be a bit different. We have a sum. We're adding this and this. So when you have two things that are added together and you are finding the derivative of the sum, you can distribute the derivative sign. You can distribute. So you can say you're finding the derivative of x squared plus the derivative of sine xy. And by the way, this is one of those examples where you can't make y the subject, and therefore you can't use the other method. You have to use implicit differentiation. Now we have this. We still need to find dy on dx. We are not done. So here there's nothing we can do. Here we can simplify. So 2y dy on dx is equal to, what's the derivative of x squared? It's 2x, because you multiply this coefficient by 2 and you minus 1 on the exponent. Then we come to this side. We are looking for the derivative of sine xy. This has an outside function, which is sine of something, and then it has an inside function, which is x times y, and then it has a function again, which is y. It's a bit tricky, but you get used to it. So the first function is sine of something, the second function is xy, and the third function is just y. So we will use the chain rule here. We first differentiate the outside, which is sine, and the derivative of sine of something is cos of that thing, xy. Now let's differentiate the inside. So we have to multiply this by the differentiation of the inside. And if you look at the inside, you are multiplying x and y. Because it's xy. If it's xy, that means they're multiplied. So what we use there, if two things are multiplied, is the product rule. The product rule says you take this and you multiply it by the derivative of the second one, the derivative of y. That will be dy on dx. And you add that to the derivative of okay, we took this, we multiplied by the derivative of this. Now we are taking y and we are multiplying it by the derivative of x with respect to x. Okay, we are getting somewhere. There's let me not complicate things. Bring this down as it is for now, and you have 2x. Then this is where we are going to have the fun. Now this has to be distributed because cos xy is being multiplied by this bracket. Yeah, so this cos xy is going to multiply here in the sorry. So this is gonna come there, which is gonna give us x dy on dx cos xy. right? And when it comes to this side, firstly, before we multiply by cos, we are looking for the derivative of x with respect to x. How is x changing with respect to x? It's changing, that's 1, because they are both the same value for every value of x. Oh, I should have put d here, sorry. Or you could just say they're cancelling out, but I don't know if that's... Just say it's 1. So the derivative of x is 1, though. You know that. I don't need to complicate things. Now this is just y, that means. So we'll multiply it by cos xy. So it's y times cos xy. Now we need to make dy on dx the subject of the formula. So to do that, we need to transpose this into that side. I think that's the easier way. So we'll have 2y dy on dx minus x dy on dx cos xy is equal to 2x plus y cos xy. We take dy on dx as a common factor this side. Dy on dx into 2y minus x cos xy is equal to 2x plus y cos xy. Now we divide by 2y minus x cos y x. 2y minus x cos xy, 2y minus x cos xy. These cancel out and you have the derivative of y with respect to x as x plus y cos xy divided by 2y minus x cos xy. Okay, that is your answer. That's your answer. Hope you understood that. We were looking for the derivative of this, or the derivative with respect to x of this function y, and we found that the derivative is this. So let's go to another question. The next question says we should find the derivative of x squared y plus x y squared is equal to 6. For the derivative here, once again, you find the derivative of this side, d on dx of x squared y plus x y squared is equal to d on dx of 6. Now let's start with this side. Well, okay, we can start with this. D on dx of 6, the derivative of any constant is 0. So basically this side is equal to 0. Here, we will distribute the derivative sign. So when you take it to the first one, you have d on dx of x squared y plus d on dx of x y squared is equal to 0. Now we need to find the derivative of this, and this is a product. We will use the product rule. Notice how if you only have you just have y, you don't have y squared or any exponent of y or any other thing disturbing y, we just take dy on dx as the derivative of this y. But if it was y squared, it would be a different story. So we use the products rule here, which says if we are looking for the derivative of x squared times y, you'll say x squared times the derivative of y plus y times the derivative of x squared. right? That's the product rule this side. Plus, we're getting to this now. Use the product rule once again. Now it's squared, so it will be a bit different when we are differentiating. We are looking for x times the derivative of y squared plus y squared times the derivative of x, which is equal to 0. Now we are simplifying now and substituting the derivatives. We know we have x squared. We can't do anything with dy and dx, and that is what we are looking for anyways. So we sub back dy and dx plus here we have y, this one, and we are looking for the derivative of x, that is 2x, plus we're getting here now we have x, and we want the derivative of y. Remember once again, y is a function, and therefore this is a composite function. There's a function called y, or there's a function y, and there's also another function y squared. So we first differentiate the outside function, which is y squared, and we get 2y, and then we differentiate the inner function, which is y, and we get dy on dx. We are done with this one. This is the derivative of this, and then we go to the next one, which is y squared plus this is just dx on dx, which is 1, and the derivative of x is 1 anyways, and we equate that to 0. Now we want to make dy on dx the subject of our formula, so we'll pull this closer to this side, just so we can do that in an easier way, and transpose the others to the other side. We have x squared dy on dx plus 2xy dy on dx, right? 2xy dy on dx is equal to negative 2xy minus y squared when you transpose it. Now we take out dy on dx as a common factor, dy on dx, because it's here and it's there. We are left with x squared plus this side we have 2y x. Should have said 2xy, but minus 2xy minus y squared. Now we just divide by this guy, x squared plus 2yx, x squared plus 2xy. This goes away, you have dy on dx as negative 2xy minus y squared divided by x squared plus 2y. That's your answer. Now we are doing another one. The next one we are doing is we have to differentiate x squared into x minus y all squared is equal to x squared minus y squared. So there's several ways you can approach this, but I think you should get to the same answer. In fact, if the world is real and round and science is true, then it should definitely get you to the same answer. Last time I did it another way, but this time I want to take out this squared out. Let me show you right now. X minus y all squared, right? Because if you were to remove the brackets, the squares would have to be distributed. I want to see how fun this way will be. Now we need to find the derivative of this, and if we're differentiating using the implicit differentiation method, we find d on dx of both sides. So d on dx of this side, x into x minus y all squared is equal to d on dx into x squared minus y squared. Now let's differentiate both sides. To differentiate this side, we have a product, but we also have a squared there. So we'd have to use the chain rule for this, since we have a function and that function is squared. So we first differentiate the outside, which is basically the square bracket squared. So that will be 2 multiplied by x into x minus y, and then you'd say 2 minus 1, you get 1 as the exponent, and you've differentiated the outside. Now let's get to differentiating the inside. When you differentiate the inside, it's a product. This is getting very complex, but I think I should go back to doing more product and quotient rule videos. But this is a product, right? You're multiplying x by x minus 1, which means if you like, you can distribute and do it that way, but we're gonna do it the hard way, which is the product rule. For the product rule, you say x multiplied by the derivative of this, d on dx of x minus y, plus x minus y multiplied by the derivative of x, dx on dx, and we equate that to the derivative of this side. The derivative of this side is you just distribute the derivative sign. You have d on dx of x squared minus d on dx of y squared. Okay, so this is fine. Let's just distribute the 2 into the inside. So we have, or let's distribute the 2x, because this is 2x multiplying into this. We have 2x squared minus 2xy. 2x squared, 2xy. Let's get inside here. We have x. We distribute the derivative sign. If you take the derivative sign there, right, let's move a bit faster. If you take the derivative sign there, you'll be looking for the derivative of x. We already know the derivative of x to be 1. If you take the derivative sign there, you'll be looking for the derivative of y. We know the derivative of y with respect to x is just dy on dx. We move on to the next one. Here this is 1. The derivative of x with respect to x is 1. So you have x minus y, sorry, which is equivalent to, now let's come to this side. This side we're differentiating x squared with respect to x. That's 2x, power rule. Now let's differentiate y squared. We already know y squared, if you differentiate it, the outside will give us 2y. The inside gives us dy on dx. Once again, let's try to distribute everything so that at the end we can have dy on dx as a subject of the formula. I'll try to move a bit faster on this one because this is not the main focus of the video. So we have 2x squared minus 2xy, x minus x dy on dx. Shoot. Plus x minus y. And then you have 2x minus 2y dy on dx. I just distributed the x. Now this is x plus x, which is 2x. So now we have 2x squared minus 2xy, 2x minus y minus x dy on dx is equal to 2 minus 2y dy on dx. Right, now we need to distribute this guy over to the others. Oh, I forgot to put the x there. So now we have to distribute this. I think this way is way longer than the one I used before. We distribute, we have x this times this, which gives us 4x to the fourth, or to the third power. This times this, it gives us 2x squared y minus 2x cubed dy on dx. Now we'll do that. Minus 4x squared y plus 2x y squared minus 2x squared y dy on dx is equal to 2x minus 2y dy on dx. Okay, that was a long journey. Let's transpose everything with dy on dx to one side. I'm just thinking which side will be better. Let's transpose it to that side, right? That side, right hand side. Here we'll be left with 4x squared minus 2, or x cubed, 2x squared y. This is gonna go to that side. We have minus 4x squared y. Okay, should have added these. I'm gonna add them now. And we have plus 2x y squared. This is gonna go that side, but this will be brought back this side. We have minus 2x, and this is equal to, we have transposed this guy to that side and this guy to that side, and this guy would be positive this side. It'd be positive 2x cubed dy on dx plus 2x squared y dy on dx. This is that guy. Minus, now we're with this guy, 2y dy on dx. Okay. Now we need to take out dy on dx as a common factor from these guys, and this has a factor of 2, this has a factor of 2, this has a factor of 2, this has a factor of 2. This is going to be 6, and it will have a factor of 2. This has a factor of 2, this has a factor of 2. So let's just take out 2 from the entire thing. Yeah, this will be divided by 2. We have 2 x cubed minus, if we add these, we'll have 6, and then if we divide them by 2, we have 3 x squared y. We come here, have plus, we divided by 2, so we left with x y squared. We divide this by 2, we just left with minus x. We divide everything by 2, so let's ignore all the 2's. We take out dy on dx as a common factor. Here we'll be left with 2x cubed. Here we'll be left with 2x squared y. Here we'll be left with minus, oh shoot. Look at me. no twos, minus y. And then you divide by this guy on this side, x squared plus y, x squared minus y, and divide by him on this side too, x squared plus y, x squared minus y. This cancels out, and therefore dy on dx is equal to 2x cubed minus 3x squared y plus x y squared minus x divided by x squared plus y x squared minus y. That's your answer. That is your answer. Let's move on to the next one. I'll do two more just to keep the video short, but I think this video deserved a lot more examples. Okay, so the one we'll do now is, which one should we do? Let's do trig. Let's say I have x equal to sec xy. So we have to use implicit differentiation to differentiate this. So how you do that is you say, well, x, you find the derivative of both sides, this just cancels out. Then I don't think I should have dragged that division sign all over the place. This side gives us 1. But what happens to this side? We have d on dx of sec x y. But we can't directly differentiate sec, or at least from what we know so far, from what we've learned. So let's change sec to be its co-function, which is cos. So it'll be 1 over cos xy, and then we'll differentiate this. And if we are differentiating this, it's a bit easier, but a bit hard at the same time. How is it easier? We know what the derivative of cos is. How is it harder? It's a fraction, and therefore we have to use the quotient rule. How do we use the quotient rule here? Well, the quotient rule says you take the bottom one and multiply it with the derivative of the top. So you would have had cos xy times the derivative of 1. But we know that the derivative of any constant is 0. So if the derivative of the constant is going to be 0, this whole term is going to be 0. Please watch the video on the quotient rule to understand this, because if you don't know the quotient rule, you won't understand this part. And then the second term would have been minus 1 multiplied by the derivative of the bottom, du and dx of cos xy. Right? We don't have to write the 1 because it's not. You understand. And then at the bottom, using the quotient rule once again, you need to square the bottom xy. Now we need to find the derivative of the top. How we do that is we say we have two functions at the top. There's the cosine of something as well as the inner function, which is x times y. You could say there's 3 functions because it's cosine of something, then there's x times y, and then there's y. Y is a function too. It's not just a variable. It's a variable function. Right. So we differentiate the outside, we get negative sine xy, because the derivative of cos is sine, we go to the inside, we use the product rule to differentiate. So we say the derivative of x is 1 times y plus the derivative of y is dy on dx times x all divided by cos squared xy. You can multiply by cos squared xy on both sides. You get cos squared xy is equal to, this will give us a positive sine xy into y plus x dy and dx. I wrote the x on the front because it looks neater. Now we want to make dy and dx the subject of the formula. There are two ways we can do this, but I think the easier way is to just divide by sine xy on both sides. Well, there are probably more than two ways, but there are two ways I can think of right now. Sine xy. This will cancel with that. And this, we know we have cos xy times cos xy divided by sine xy is equal to, this is just y plus x dy on dx. We are still trying to make dy and dx the subject. Here we got things easier. We have cos over sine, that's cotangent, because this is the reciprocal of tan, and therefore it has to be cot. So we have cos xy, which is this one, multiplied by cotangent xy, which is this one, minus this y is equal to x dy on dx. Now we just need to divide by x on both sides, and then we are done. We are done now. Dy on dx is equal to cos xy cot xy minus y all divided by x. And that is your answer. Just one more and then we will be done. The next one is y sine 1 over x is equal to 1 plus x squared y. Okay, so we're doing this one. For this one, once again, as always, you find dy, we find dy and dx of both sides. Actually, here you can make one y the subject, but we are still going to use implicit differentiation. dy and dx. Right, so we are multiplying this function by this function, and therefore we should use the product rule. The product rule says y times d on dx of sine 1 over x plus sine 1 over x times d on dx of y. And then this side, the derivative of 1 is 0. We find the derivative. This will actually be the equivalent to the derivative of x squared y. Now this is a product once again. So for the product, we want x squared times the derivative of y with respect to x. In my handwriting, I don't know why, but it will be fine. And then we have y times the derivative of x squared. Now let's start here. Y, the derivative of sine. We know there's an outside function which is a sine, and that the derivative of that is cos 1 over x. We look for the inside function, which is 1 over x. The derivative of that will be found using the quotient rule. We say x times the derivative of 1, which is 0, minus 1 times the derivative of x, which is 1, because the derivative of x is 1, divided by x squared. And then we come to this side. There's not, okay, we have plus. There's nothing we can do to 1 over x and sine, or there's nothing we should do. We have d on dx. There's nothing we can do with that either. We have here x squared dy on dx. Nothing can be done. Plus, what's the derivative of x squared? It's 2x. Now we are just simplifying now. This term and this term are the ones that have dy on dx. We want them to be on one side. So I'm going to transpose this guy to that right hand side, and I'm going to transpose this guy to this side. But let's first simplify here. This is 0, doesn't matter. This is negative 1, so this is negative 1 over x squared. Negative 1 over x squared, so we have y cos 1 over x times negative 1 over x squared. This will be transposed to that side, but this will be transposed to the left hand side, 2x, equivalent to x squared, this one, times dy and dx, minus sine 1 over x, dy and dx, this one transposed to that side. Now let us multiply this out. This will give us a negative y cos 1 over x, all divided by x squared. Because you multiply all the numerators together, you multiply the denominators together. Minus 2x is equivalent to, you take out dy and dx as a common factor there, dy on dx. You add x squared minus sine 1 over x. And then you divide by this entire bracket on both sides. You have d on dx, dy on dx rather, as negative y cos 1 over x, all divided by x squared, minus 2x divided by x squared minus sine 1 over x. Right, I'm gonna leave this there, but there is further simplification that can be done. You can take this and bring it there, take this and bring it there. But for this video, I'm done. Thank you for watching. Subscribe. See you on the next one.